Hi everyone, hope you're all doing great. So welcome to our channel of Sciences and Mathematics. I'll request for those of us who have not yet subscribed, kindly go to YouTube, search Sciences and Mathematics, subscribe to our channel and also hit that notification button so that you can be getting updates as we try to discuss and gain new skills both in Sciences and Mathematics. So also you can be active on our comment section so that our larger family of Sciences and Mathematics members can be able to share and try to assist one another. So today's topic will be a very interesting one. Of course, it will be a concept in physics, particularly modern physics, under the topic of quantum mechanics. This particular concept is very important because it's going to assist us and form a basis in understanding other concepts which we are going to learn in quantum mechanics and related topics. So for today, thank you and welcome. Feel free to question in the comment section and also contribute. So thank you. So as we have said, we're going to learn about a concept in modern physics. And this concept will be under the topic of quantum mechanics. And the concept will be the de Broglie's hypothesis, a de Broglie's equation. Now, as I've stated, this particular concept is very important because it's going to form a basis for us in understanding some of the concepts that we're going to learn. So remember, as a quick recap, the last time we talked about this particular concept of modern physics, we stated that physics itself as a subject is divided into two basic branches, that is modern physics and then classical physics. Classical physics is the one that was developed over time up to the end of the 19th century, while modern physics is a branch that developed from the beginning of the 20th century up to date. So in that case, you will find that modern physics relies on two specific theories which are very important, of course, in understanding what modern physics deals with. The first one is the theory of relativity that was developed by Albert Einstein in 1905. So the theory of relativity. This was done by Albert Einstein in 1905. And then the second one is quantum mechanics. So as we go along, we shall discuss about these particular concepts or the theories which were very fundamental in the development of modern physics. But as now we are going to look at this under the topic of quantum mechanics, the de Broglie's equation. So for that case, bear in mind that we also have this particular section that we are going to cover, which complements the concepts which are being developed here for us to have a full picture of what modern physics really entails. Of course, there will be a correlation between different topics as we go by, but as of now, that will be our scope. So fast forward, now we shall go to, so this one we shall have a quick reminder for ourselves so that we cannot forget what we learned. So the last time we talked about quantum, we said that a quantum is a packet of discrete units, or in this case we can refer quantum to discrete packets or bundle of physical entities. So these are discrete packets, bundles, and in this case we can say these bundles of entities. So in this case, entities can refer to either maybe we can say objects can be even energy. So in this case, we are going to find that whatever we're going to discuss is going to be biased, particularly on that aspect. So, but the main thing that we were going to look at here is what the term quantum refers to, and mechanics, we say the study of motion. So for that case, we are going to deal with this particular aspect of quantum mechanics and just try to observe a few things and then we will proceed. So this is very important for us to understand, because this came about after scientists had performed different experiments and actually discovered that as we have different laws which are applicable in classical physics, which deals with, especially on the part of motional mechanics, deals with objects which are observable, which are at the intuitive level, of course, which we can be able to see, observe. So in this case, quantum mechanics deals with objects which are very small and move at a very high speed. So for that case, it deviates from the aspect of quantum mechanics, of course, because it has been observed that the subatomic particles behave in a different way as we could expect those ones to behave in classical physics. So as we can see, that necessitated the development of quantum mechanics, because as we know that particles in classical physics, they have specific laws which they follow, for instance, the Newtonian laws, but in quantum mechanics, they are going to violate some of these laws. So which means we have to develop a different way in which we are going to treat this particular small and very fast objects. So that case, that is what led to the development of the concepts such as the one that we are supposed to discuss today, as the de Broglie's hypothesis. Now, someone may ask, what is an hypothesis? So our major or main topic of concern or concept today is the de Broglie. De Broglie's hypothesis. So why are we interested in the de Broglie's hypothesis? Now, Louis de Broglie observed that or postulated that in as much as the particles, the small particles, are behaving as particles. Remember, we talked about subatomic particles such as electrons. This one can as well be atoms, because we cannot be able to observe them by our naked eyes. Molecules, etc. And other particles that fall under this class are very small, and it was observed that their motion is quite characteristic. It's different from the ones we can observe in classical physics. Now, we may ask ourselves, the de Broglie's hypothesis, of course, in scientific methods, we have different terms that are being used there. We have scientific laws, we have principles, for instance, the Newtonian laws of motion, we have maybe the gas laws, scientific laws, those are scientific laws, principles, etc. So in this case, we are talking about an hypothesis, and for us to have a quick reminder, an hypothesis refers to as an intelligent guess or an educated guess. But for instance, okay, for this case, we just have just a simple definition for this, and say that an hypothesis is a testable statement that describes how something works or behaves. in a natural world. So an hypothesis is a statement, a testable statement that describes how something works or behaves in the natural world. So the word testable is being used here intentionally, of course, which means if an hypothesis has been forwarded, then it can be tested to see whether it holds or not. In this case, you can test an hypothesis by doing an experiment. So in this case, the de Broglie's hypothesis, it's a testable statement that describes how something works in the natural world. So in this case, of course, Louis de Broglie is going to make a claim, or maybe the hypothesis that we're talking about, that just like light, particles can behave as waves and as particles. So which means de Broglie is trying to compare an aspect of light which is being seen to behave as particles and as waves. Remember that light, just like electromagnetic waves, display some properties of waves like interference, diffraction, and other properties. So for that case, those ones give light the property or the aspect of behaving like waves. So when light is being compared to particles at the smallest level, remember we have said that quantum mechanics deal with particles, very small particles that move at a very high speed. So for that case, particles, as per the Louis de Broglie's argument, particles can behave as waves and as particles. So which means they display the two properties which we are going to look at shortly. So under this Louis de Broglie's argument, it's better for us to look at the properties of light, the properties of particles and waves. We compare them with the properties of waves at the same time, in summary, so that we can see which are some of these aspects which are being compared to, and in actual sense they are trying to match or they are trying to agree. So for that case, if we try to look at the properties of waves, we will see that waves, especially transverse waves, contain or display the property of a wavelength, denoted by this one lambda, and they have what we call frequency, denoted by this particular letter, and then they have what we call wave velocity, denoted as such, that is omega, and then they have amplitude, denoted by capital A, and then they have phase and intensity, that is phase, denoted as this, and then intensity. Those are some of the properties of waves. Now, in comparison to the properties of particles, particles have mass, denoted as m, and then they display what we call a velocity when in motion, denoted as that, and then they possess momentum when in motion, given as p, and then lastly we can say that particles also possess energy when in motion, denoted as capital E. So in this case, if we are trying to look at the Louis de Broglie's hypothesis, is trying to claim that his claim is actually that particles can behave as waves as behaving the same time as particles. So they have a correlation for that. So we are trying to look at the properties of these particular two aspects of nature so that we can see whether these properties which are being displayed, do they equally hold, or maybe what is happening here. So for that case, as we say, the hypothesis is a testable statement. We're going to do some of the experiments. So try to look some of the evidence which have backed up maybe Louis-de-Broglie's hypothesis to claim that light can behave as waves, or maybe particles can behave as waves and waves as particles at the same time. So have in mind that these are some of the properties of the waves and particles in comparison, so that we can be able to, wherever we come across them in our topic, we are able to do the relationship, get the concept. So in that case, the properties that we have mentioned are going to be very much essential, because as we develop the Louis-de-Broglie's claim, it's going to assist us in understanding the wave-particle duality. So his argument was that when particles are accelerated, they spread out like waves with a certain wavelength given as lambda. So these are particles accelerating. Maybe they are moving in that direction. He says that when they spread out, for instance, this is the point of origin, or maybe they are at this point, and maybe they are being spread out. His argument was that when they are accelerated, they spread out like a wave with a certain wavelength lambda. So as we can know that our previous discussion was that lambda, this is a wavelength given as lambda, is one of the properties of waves. So therefore his argument was that when particles are accelerated, they spread out like a wave with a certain wavelength lambda. Now, Louis-de-Broglie's argument, we're going to see this in the form of an equation, or some of the experiments or the fundamental basis upon which he built his argument. Of course, this relies on works of various scientists who had performed and confirmed some experiments before, and they had come up with some of the laws or relationships between the waves that we have discussed and particles. These relies on the properties that we have listed on the board. Of course, this approach relied on, this is Max Planck, and Albert Einstein. I forgive my handwriting. I hope it is legible. So this concept of the Louis-de-Broglie's hypothesis relies on Max Planck and Albert Einstein's energy-mass relationship. So we can ask ourselves, of course we're going to learn in depth about these two particular relationships, but Max Planck was studying the black body spectrum, and they argued that the oscillators the black body is made up of a large number of oscillators which are vibrating at the characteristic frequency, and they argued that the energy of an oscillator can be given as hf, where h represents Planck's constant, and f is the frequency of the vibrating oscillator. Of course, we're going to learn about these oscillators when we're going to discuss about the Planck's quantum theory, but for this case, we're just going to mention them. So Planck's argument was that energy is equals hf, where h represents Planck's constant and f represents the frequency of the vibrating oscillator. While Einstein, on his part, did an extensive study on the photoelectric effect, energy is given as mc squared. So in this case, Einstein's energy mass relationship, of course this one, m represents the mass of the particle, as we see that one of the characteristics of particles is that they contain mass. So for that case, this one represents mass of the particle, and then c, this is the speed of light. So in this case, if you can see the relationship that we talked about the light behaving as particles or waves, and then waves behaving as particles, there's a relationship in a sense that light falls under the electromagnetic spectrum, then all the range of the spectrum consists or displays similar amount of speed, which is the speed of light. So for that case, there's an argument that particles that are traveling at a very high speed, there's of course some conditions that we're going to give when we shall learn about quantum mechanics. But for this case, these are the relationship between Max Planck and Einstein's energy mass relationships. So we're going to look at these equations and try to see really how de Broglie hypothesized about the behavior of these particular particles that were behaving the same as waves. So remember this relationship between these two, where de Broglie put this basis of arguing that light behaves as waves, or particles behave as waves, and waves behave as particles. So in this case, we are going to look at, just in a nutshell, some of the, specifically the 3 experiments that were used to confirm this wave-particle duality. So there were experiments that were performed in order to verify or try to see whether actually these waves can behave as particles or particles can behave as waves. The first experiment, of course, that was done was a double slit experiment. The second one that was performed was photoelectric effect that we had mentioned. And the one, of course, there are some of the experiments that might not be mentioned here, which back up this concept, but these are the main experiments that we're going to discuss. So the last one is the Compton effect. So in this first case, this was an experiment that was done to determine whether waves can behave as particles or particles that are accelerated can behave as waves. This is a double slit experiment. Not a long stretch for us to demonstrate, but we shall discuss about it in details. So it was shown that when a beam of rays was directed towards, this is a beam, this is a slit here. I don't know whether it's visible. We just put those dashes to imply that there's a space here. So this is a slit. When it's directed at that point, you'll find that the waves will start spreading out in a way that if a screen is put on this other side, there will be points whereby there will be some light seen, darkness, light, darkness, fringes will be formed on this particular screen, of course. So in this case, you'll find that there will be areas of maximum displacement and minimum displacement, and those points keep on repeating themselves in an alternative way, in a way that this is a property that we see that was being displayed by transverse waves of of course, which have got amplitude that we talked about the properties of light. For instance, this is an maximum displacement from the point of equilibrium. So this one will be an amplitude. So from here to here is a wavelength. So you can see that this is a property of waves. This is a beam. So in this case, this one verifies that light can behave as waves. So if a beam, this is a beam of light. So if a beam of electrons at the same time, electrons, remember we talked of them as subatomic particles, is just directed here, the same property will be observed. So which means these electrons, which are particles, just behave as waves. So this is an experiment that has been performed and confirmed to be working in the same way. So this is the first experiment that was performed to confirm that particles can behave as waves and waves can behave as particles. The second experiment that was done is a photoelectric effect, whereby if a beam of light is shown on a metal surface, this is a metal surface, you will find that at a particular frequency, some electrons will be ejected from the surface of the metal. So this, what does this one explain to us? When we are going to, or when in our topic of motion, or maybe when we shall start about work, energy and force, we will find that motion of particles that we talked about in classical physics, they have what we call momentum. Of course, we talked about them as a property of particles. So in this case, when a particle that is in motion, it possesses momentum. So in that case, when it lands on the surface, it's able to knock other particles. So which case, this case displays that this beam of light is behaving as particles that we study in classical physics, which possess momentum. Of course, is the one which are able to give energy to another particle for us, for it to enable it possess energy to assume motion. So for that case, this experiment, the photoelectric effect that was observed in this experiment, gave an evidence that actually a beam of light shown on a metal surface was able to knock out electrons, which means it possesses momentum. So in that case, this beam of light is behaving as a particle. Of course, we said that light is considered as a wave. So you can see the relationship between the particle, wave, the beam of light that has been shown there. The last experiment that was performed by Arthur Compton, of course, this is way back in the late 20th century, early and mid 20th century. It was performed by Arthur Compton, and it was observed that in quantum mechanics, the momentum that I've talked about, which is a characteristic of particles, is conserved. So in classical physics, the law of conservation of momentum, so this is it was observed that momentum is conserved also in quantum mechanics, and this is a law that is obeyed, of course, as I've said, in classical physics. This was done by finding evidence from scattering of X-ray photons by electrons. So scattering of X-ray photons by electrons confirmed that actually in quantum mechanics, momentum is conserved. Now, for instance, if I can give a small demonstration here for the same. Say that here we have an incident photon. Incident means which is coming on this surface. And then it comes across that particular particle there that we've said. Just draw it there. So this is an instant. A photon, this is a particle that contains energy that we talked about being represented as E is equals hf, where h is Planck's constant and f is the frequency. So that one can be considered, or is just an analogous to the beam that we have discussed before. So you'll find that the effect of this will be that there will be scattering at an angle, let's say maybe angle theta, and then another one at angle alpha. So in this case, you'll find that the value of the photon momentum, this is a photon, the value of photon momentum will be given by h over lambda, which of course we're going to see that that's our next part, which is being given as described by Louis de Broglie. So in this case, you find that just like electromagnetic radiation, photons undergo diffraction and interference, which confirms the aspect of particle-wave duality. Duality, in a sense, means that they are displaying properties of both waves and particles. So in this case, we confirm that photons and matter both have momentum, and electromagnetic radiations have particle properties. So these particular three experiments were very important. Of course, they assisted us in describing some of these properties of particles which are being displaced, whereby they behave as waves, or waves behaving as particles. So then what is the Louis de Broglie's hypothesis, of course, in form of an equation? What was de Broglie actually trying to describe? So if we look at the relationship that we discussed about, the Planck-Einstein energy mass relationship, E is equals mc squared. Of course, these initials we discussed where they present energy is equals mass times the speed of light squared, or mass, the product of mass and the speed of light squared. And then this is according to Einstein. Now for Planck, A is equals hf. Of course, we are going to see later that this frequency is represented as c over lambda, trying to look at the relationship between the initials which are being given here. So then, as we proceed, this is the mass, as we said, and this is the Planck's constant. F represents the frequency. Frequency, this is C. And then lambda, this is the wavelength. And then what have I left out? Mass, wavelength. C is the speed of light. So mass m, h represents lambda, h represents Planck's constant, f represents frequency, which can be given as c over lambda. Lambda is wavelength, c is the speed of light. So this is the relationship between those particular two concepts. So if we were trying to find the relationship between the two, then it is correct for us to say E is equals h v. Of of course, the frequency now is represented by this one. Remember when we were talking about the waves, the waves, properties of waves, we were giving that one as V. So V equals C over lambda. So in this case, is equals hv, which is the same as mc squared. From classical physics, we know that momentum is given as pv. No. mv, mass is the velocity. So in this case, remember there is a difference between this one and this. This one actually is, the initial for this is given as like this. It's quite different from that one. This is a frequency where this is the velocity. So in this case, if we try to see Einstein's mass energy relationship, then therefore we can say that H frequency equals mc c. Now the relationship between this one and this, in this case you'll find that mc will represent the the momentum of a particle that is moving and being described by Einstein's energy mass relationship. So for that case, we can substitute for that and say that of course, let me just erase that one so that we can use this space. Therefore, we can say that, remember, we can do a substitute for this frequency and say that hc over lambda. Now, whereby this one represents the frequency that I've just written here, c over lambda is equals mc dot c. This is c squared. But this one represents momentum p, so we can relate the equation and say hc over lambda is equals just to do away with this, pc. So c and c will cancel out, and then we'll find that making lambda the subject of the formula, we'll find that lambda is equals h over p, Planck's constant over the momentum, and this one represents the de Broglie's equation. De Broglie's equation that was trying to describe these particular particles which are behaving as waves. So this one gives the wavelength of a particle that is being accelerated or maybe in motion, and these particles are particles which are using the laws of quantum mechanics, which are small and very high speed. So for that case, that is the concept that we are looking for. So in a quick recap, we have said that there is a relationship between particles and waves, and these particles and waves, according to de Broglie, who used the Planck-Einstein's mass energy relationship, can be the momentum of that particular particle, as we have done the substitution here, can be represented by using lambda is equals Planck's constant over the momentum. So for that case, I thank you very much for this lesson. I welcome you as we proceed to discuss some other parts or aspects of quantum mechanics. Of course, as we go by, we shall be solving some of the problems that we may encounter, or doing an example or two as we discuss in this topic. Of course, we shall be doing much of theory, and then later we shall be doing some of the practices for us to understand this concept. So for today, thank you, welcome, God bless you, bye.